currently of Rivers Security Services. But prior to that, 35 years of experience working in nuclear safeguards and security in the DOE and NRC and related organizations. And he comes at this from a slightly different background from many of us. He's not a nuclear engineer by training, but a background in mathematics and statistics from RPI and then Penn State. And applying that interesting skills to this question of nuclear security, categorizing material and facilities, looking at risk-informed aspects of that, and so on. So I'll leave it there and allow Joe to fill us in on all the details, and welcome him to begin his presentation.
Well, it's a pleasure to have the opportunity to speak with you all today. I've given a lot of these risk-informed talks at other schools like Penn State and University of Tennessee. And it just gives you some insight into, I know in your nuclear engineering work, you're doing a lot of risk-informed work with PRAs and things like that, but in security, we actually use risk information almost all the time. But what I've done here is I've set up a talk that'll give you a little bit of background about what nuclear security is, and then go into about 4 different areas that give you some ideas of the diversity of how the security community actually looks at risk information. So let's start out with a bit about nuclear security. And essentially NRC activities and the design basis threat. So there's a lot of, a second, I think I skipped a slide there. Okay. Purpose of NRC regulated physical protection. So essentially NRC looks at the requirements are in 10 CFR 73. So it's a very narrow part of the Code of Federal Regulations. And they're established for the maintained physical protection systems, and that the focus is on protecting the public health and safety, the environment, and the common defense and security. And NRC looks at protection of the special nuclear material at fixed sites, which include nuclear power plants, research and test reactors, fuel cycle facilities, and also in transit between plants. So it covers a fairly broad spectrum. Then they also cover the protection of radiological material as well. So one of the things that most people hear about in the security world is the design basis threat. It has a lot of similarity to the design basis accident. It's essentially, how do I design my physical protection program, and what is the threat that I have to be concerned about? Essentially, if the threat is actually larger than that, there's an expectation that the state would provide protection to that part that's above that level. And so NRC breaks things into high-risk activities and lower-risk activities, and so you see the term risk there. And so a design basis threat defines how many bad guys are coming to attack, what their equipment is, what their techniques are, what their tactics, what their motivation, and what their objectives are. And so you can see in this slide that essentially the design basis threat applies to power reactors, high enriched uranium and MOX fuel production, and as well as the transportation of these materials between facilities. Lower risk activities, although DBTs do not apply, we essentially make an assessment of what that threat is and develop protection requirements based on what we perceive the threat to be. And this would include low enriched uranium fuel fab facilities, some of the things that are coming online now, like the high assay low enriched uranium facilities that are producing fuel for advanced reactors and small modular reactors, the transport of low enriched uranium, and also spent fuel storage and transport. So one of the things that we look at is that the 2 most significant types of facilities are the power reactors and Category 1 fuel cycle facilities. And those would be the high enriched uranium facilities, and if there happened to be a plutonium or a MOX facility. And you'll find that in general, the protection, the security type protections that are applied at both of these facilities have a lot of similarities. Typically what you're looking at in physical security is barriers, controlling access, having a well-trained guard force, detection and assessment systems, alarm stations, and strategies for response. Also, we typically have an expectation these facilities will have some level of personnel security. They'll conduct some level of background checks. Fitness for duty is usually drug and alcohol testing, and then access authorization, which says you have a right to be in the facility. And then there will be information security and cybersecurity requirements as well. The expectation here is that you'll have robust structures and redundant safety and security features. Now, prior to 9/11, security was much lower at most of these facilities than we perceived before. Essentially, we did have an expectation that the adversary was willing to die and that these large groups of people might attack facilities. And so what you found post 9/11 was that there were a lot of significant security enhancements, both at nuclear power plants and fuel cycle facilities. This included the addition of more security officers with patrols and checkpoints, increased surveillance of owner-controlled and protected areas. One of the things you typically found too was that most of these facilities started buying up property outside of the land they already owned, so that they could gain earlier detection of people that might be coming in to do something malicious towards the facility. There also were increased access authorization controls, stronger background checks, enhanced barriers. There were a lot more barriers to prevent vehicle bombs from detonating close to the facility. Much more stringent search procedures. There was also a lot more concern about how many people and which people should actually gain access to different parts of the facility. There was a lot more liaison with local agencies, especially local law enforcement agencies. And there was enhanced coordination with federal agencies. You saw a lot of engagement with the Department of Homeland Security, setting up fusion centers and things of that nature. One of the things that you'll notice in most nuclear security situations, especially the higher level ones, is that they have what are called layered protection or zone protection. And so if you look at this nuclear power plant, one of the things you find is that the outer area that's behind the fence, and it's basically the owner controlled area, and that's sort of the beginning area where they're hoping to get some level of detection. Then you'll notice the inner fence there is the protected area. You'll notice it's actually a double fencing, which has an isolation zone that allows for a number of intrusion detection systems to be deployed there. And so the expectation is that you hope to find malicious people coming in the owner controlled area, but you want to be almost certain that you've caught them seen them by the time they come across the protected area boundary. And then if you get into the interior part of the facility, you get into what are called the vital areas. And those are the areas that you want to afford the highest level of protection, because if the adversary gets in there and has time to do damage, he could actually cause the reactor containment to be essentially broken and the radiation released. So one of the first topics I want to talk about is vital area identification. What is it? What are the inputs? We'll talk about initiating events of malicious origin, and we'll develop a SAGE logic model, identify candidate vital area sets, and select vital areas. The vital area identification is the process used to identify what needs to be protected at a nuclear power plant to protect against radiological sabotage. It's fed information from PRAs used for safety analysis. Typically what you're talking about are the cut sets from a PRA that identify the safety systems that, if they're not working or functioning, will essentially cause core damage. So there are a lot of inputs that go into the vital area identification. The first is the policy considerations. What is in the international guidance for radiological sabotage, there's unacceptable radiological consequences and high radiological consequences. Unacceptable radiological consequences is the threshold at which you start trying to do things to prevent it. High radiological consequences is where you have very strong regulatory requirements. So when we talk about a nuclear power plant, core damage and radiological release would result, essentially be a high radiological consequence, because the energy of the power plant will actually be pushing the radioactive material out of the facility and into the environment. You have to look at the various operational states of the reactor. So is it in, am I in a shutdown period? Am I in an operation period? What is the specific state of the reactor? What is a safe facility state? That's usually defined by the regulatory authority. And then, of course, the design basis threat identifies what is the threat that you're protecting against. Then look at your site and facility characteristics. What's the population density in the vicinity of the facility? The locations, inventory forms, characteristics, and quantities of nuclear and radioactive material. Also look at the critical safety functions that have to be prevented for HRCs. So essentially, what are the safety features of this plant that I need to protect to keep it operating in a safe fashion? And then what are the potential radiological consequences? Conservative analysis should be performed without consideration of physical protection and mitigation measures. So essentially, this helps you identify what I have to protect and where I need to put mitigation measures in. So I don't want to consider those as I develop what the vital area should be. So what is an initiating event of malicious origin? One of the things to keep in mind is that typically when you're dealing with, I've seen it recently, especially with the advanced reactor community, and they talk about the fact that their safety analysis has demonstrated that they won't have a significant release if the worst thing happens. The problem is that the safety scenarios that are analyzed in the PRA may be different than the actual security scenarios that take place. The safety scenarios don't look at explosives going off. They don't look at people that are creating non-random events that are taking out safety features. So we're looking at initiating events that have been assessed in a safety analysis that could have malicious origins. And we're also looking at those that involve energy sources for dispersal, such as explosives. The initiating events excluded from safety analysis due to their low likelihood, such as multiple independent IEMEOs or massive breaches or failures of passive components, although unlikely to occur randomly, could be performed by a malicious adversary. So some of the breaks of large pipes and things of that nature might not happen in a random fashion, but might very well happen when you talk about the adversary actually doing something. Other sources of potential radioactive release beyond core damage, such as irradiated fuel or radioactive waste. So the areas that we look at in a nuclear power plant would be the spent fuel pool. IEMOs that exceed mitigating system capability are of major concern, because if they actually are exercised, we don't have the ability to mitigate their consequences. And the same thing with the physical protection systems as well, if we can't protect against the threat. So we develop a sabotage logic model. Basically, we look at the capability of the threat to perform a sabotage event. If the event is beyond the threat capability, we eliminate that event from the beginning. Then we identify events beyond the capability of the physical protection system and prevent it. We collect data and we look at essentially to identify the areas of the facility where the events can be initiated. And usually you do a walk down of the facility to actually look at this, so you can identify with vital areas. It's not as much you're really trying to find areas of the plant that need the physical protection. So we verify areas where direct dispersal can be achieved. That would be things like the spent fuel pool. We verify sets of areas where threat can accomplish each IEMO. So that might be some pump systems or piping. We verify areas where threat can disable equipment systems, etc. And then we look also at spatial interactions. So we want to look at things that might be in adjacent areas that could impact other systems in an area, such as flooding, fires, and other things. So this gives you an idea of what a logic model branch might look like in a logic analysis. This is the Lone Pine nuclear power plant. The Lone Pine nuclear power plant was initially developed by Sandia National Laboratories to be able to teach in an unclassified environment security, because any real plant, the information is generally not shareable. I chaired a coordinated research project at the IEA where we further developed that power plant model, and it's been used now throughout the community to try to better communicate how do I actually do vital area analysis, how do I actually do vulnerability assessments and things of that nature. So then I identify candidate vital area sets. What you'll find is that this vital area analysis will identify probably dozens of different sets of targets. And what we have to be able to do is identify essentially what really needs to be protected and try to do it in a cost-effective manner. So the sabotage area model analyzed to determine all combinations of areas an adversary would need to access in order to complete a sabotage scenario. Each such combination of areas is a minimal cut set of the sabotage area model. So we identify from that, we develop protection sets. The sabotage area logic model is analyzed to determine the minimum combination of areas needed to protect against sabotage. And then the prevention sets are identified such that if the elements of that prevention set are successfully defended, sabotage will be prevented as well. So the vital area set selection is select a vital area set from the list of sets. It may be selected based on a number of considerations. You want to have lower impacts on safety, plant operations, and emergency response. You want to have an easier way of providing protection. You want to have a high effectiveness of providing protection, and you want to minimize the cost of actually developing a protection program. So in summary, you're using a sabotage logic model, and actually you're using a lot of the PRA type codes to actually, logic model type codes to actually to perform that analysis. And then you identify the areas of facility that, if protected, would prevent the successful sabotage of the facility. So we can talk a little bit more about that at the end, but that gives you an idea of how the security community takes the safety information out of the PRA to actually figure out how to best protect a nuclear power plant. Then we move into material attractiveness. What you find is that this is sort of the layout of the discussion here. But we want to provide an alternative to traditional approach of establishing protection thresholds based solely on the quantity of special nuclear material present. If you look at the international guidelines, it'll tell you that if I've got 2 kilograms of plutonium or 5 kilograms of uranium-235, then that's category 1 and warrants the highest level of protection. In the 1980s, the DOE was finding that it was getting very, very expensive to protect facilities and started developing approaches that looked at how attractive material was to an adversary. And in the late 1980s, actually implemented the first more graded approach to categorizing material. If you look at their categorization approach, it focuses on essentially the physical and chemical forms, the difficulty to process, and things of that nature. So one of the things you need to do is analyze special nuclear material forms to determine, can they actually be used to form improvised nuclear devices through chemical processing, machining, and things of that nature. And so what you tend to do is you develop scenarios where first the adversary must acquire the material, then process the material, fabricate a weapon, and then you have to estimate what is the actual yield of that device. Is it actually going to create a nuclear yield? And you need to determine what IND type, improvised nuclear device types that are feasible given adversary capabilities. So material attractiveness approach is risk-informed. It means of assigning security measures to special nuclear material forms based upon the intrinsic properties of material and quantities, taking into account such factors as the inherent difficulty of fabricating a weapon, requiring processing activities, nuclear physics and engineering characteristics of materials to be used in INDs, and limitations of material acquisition due to size, weight, radiation field, etc. So one of the things that we did when we looked at this was at NRC, was to actually get some help from one of the weapons laboratories to give us some insights into how to do this. And Los Alamos had developed what's called the L model, which is a logic model that they actually developed supporting NASA. It's software developed by Los Alamos to develop scenarios using complex sets of rules. It allows for comprehensive evaluation of all possible combinations of materials, forms, facility categories, adversaries, and improvised nuclear devices. The model allowed for enumeration of the permutations that satisfy stipulated constraints within the context of the model, such as the scenarios that can be output for further evaluation. Evaluation of relative importance of safeguards and security measures, as well as assessment of feasibility of the adversary designing a given device. And the model incorporated the results of the output of various physics-based models, weapons codes, and other results. It also allowed visual examination of logic flow. So the acquisition model was basically designed to look at 12 different groups of adversaries with varying capabilities and resources. The adversary capabilities and facility security measures were based on NRC DBT, the DOE Graded Security Program, and security requirements and expert input. And so we went through and used these different adversary groups and looked at a variety of facilities that needed to be considered. And we developed 32 different scenarios for each model and how the adversary might actually acquire the material. And then we said, okay, now I've acquired the material, what processing do I need to do? So we had to look at a wide variety of special nuclear material forms. They included solutions, metals, alloys, fluorides, nitrides, carbides, oxides, and hydrides. And then we looked at the processing steps, both chemical and metallurgical, of each of these forms, and evaluated them on the basis of difficulty and requisite adversary capabilities, cost, and time to process. You know, one of the things that we looked at was that the typical costs that you might see in a DOE or NRC license facility might not be appropriate. Essentially, the adversary is not as interested in safety as we might be from one of our legitimate domestic facilities. And so what my principal investigator actually did was he actually went on eBay looking for equipment that might work, even if it wasn't specifically designed for it. And things that the government facilities might spend tens or hundreds of thousands of dollars for a piece of equipment, he was able to acquire for probably in the range of $1,000 to $10,000. So that gives you some insights into, you know, what you're really looking at when an adversary is doing something. Then when we got into we had to look at the weapons physics and designs. There were numerous types of physics calculations performed, and a number of different device types were considered. And then we looked at yield reduction. One of the things that you have to be careful of is you don't assume that just because somebody builds an improvised nuclear device, it will actually detonate and produce the yield that it was designed for. So we actually developed a yield reduction model that reduced the yield based on an adversary's actual capabilities. And then in the end, what this model did was assisted us in developing an appropriate set of thresholds to establish protection strategies and measures for special nuclear material. The one thing that we did differently when we actually developed these tables for use in NRC was that we developed them to be more where you could actually have measurable values. The DOE tables, the graded security table, was really graded safeguards table was actually had a lot of qualitative type features in it, which are much more difficult to gain consensus on. So In the end, what we did at NRC was developed an approach that focused on what we call dilution levels, or essentially the weight percent of the physical component of 35, the plutonium that might be in the material. And we developed 3 different levels of dilution. One was essentially a highly dilute form, which was 1% S&M or less by weight. Then there was a moderately dilute, which was between 1% and 20 weight percent fissile. And then the final one was anything greater than 20 weight percent fissile was in the higher group. But that gives you some insights into some of the complexities that may be involved in actually trying to understand how do I actually need to protect material. The next area we wanted to move into is modeling and simulation to support vulnerability assessments. Most of you are probably very familiar with probabilistic risk assessments. What you may not know is that the vulnerability assessment modeling and simulation actually probably predates some of this PRA type analysis. This work was well underway prior to the 3 Mile Island event, and the statisticians and modelers at the national labs were actually diverted from their work in the security world to help to put together the PRA approach that could be used to help prevent future accidents like the TMI accident. But you'll see a lot of similarities between the vulnerability assessment, modeling and simulation, and PRA analysis. So modeling and simulation, why would we want to use modeling and simulation? Well, it helps us to better understand how the security elements work together. Keep in mind that it's usually focused on how they're supposed to work or how they might not work if certain functions are not working properly. It helps us understand the strengths and weaknesses of the security system, and it provides a cost-effective way to perform a systematic evaluation of security system effectiveness. What simulations don't do, they can't predict the future. They can't tell when or how an attack will occur. Simulations are not the solution by themselves. Security personnel must still perform effectively. They do not eliminate the need for force-on-force evaluations, and they do not eliminate the need for performance testing. In fact, all of these things are critical to having good modeling and simulation. So simulations are also used to understand the interactions and relationships within a complex system. People can understand and analyze system components, but are limited by the scope, scale, and personal biases. Computer simulations offer objectivity, and they can more easily assess greater scope and scale of systems. One of the things you find if you've got a really well-developed model is that a lot of times, if you think about things intuitively, you don't believe that that's the way it's going to work out. And when I was working with Los Alamos on the material attractiveness modeling, we would see something and we say, well, that doesn't make any sense. And then we would go back into the model itself, look at the rules that were used in the model, verify that the rules were accurate and correct, and then we understood why the model came up with something different than our intuitive thoughts. The same thing happens in modeling and simulation to support vulnerability assessments. You know, the systems are too complex for you to really grasp everything in your mind. You need some help from something that can do things in a structured and systematic approach. How simulations are used. So one of the things that they're commonly used for is pathway analysis. It identifies the most vulnerable pathways for an adversary, and it gives you some insights into what the probability of detection might be. It also helps you understand neutralization. It determines the outcome of an attack scenario and the probability of a neutralization. And in the end, it gives you the system effectiveness of the protection program. So other uses for simulation. Essentially, they can be used in training. They can be used as tabletop exercises. In fact, a lot of the commercial vendors for these tools are developing actually enhanced tabletop exercises that use the modeling and simulation to support it. Insider analysis, it helps you understand how an insider can actually game the system. it can be used for site visualization, so that one of the things that they use these tools for is, if I'm going to involve local law enforcement to help in my response, I can sit them in front of the computer and actually show them how they move through the facility before they actually conduct their operations. It can give you insights into sensor coverage. Do my sensors cover the area that I need to cover or not? It can do a what-if analysis. If I'm looking at buying some new sensors, some new fencing, some new barriers, the software can actually be used to say, okay, this is where I'm at now, and then if I acquire this new equipment, will that change the results of my analysis? And it can also help out in defense in depth analysis. Some of the advantages: it gives computing systems effectiveness. It also gives good insights into cost benefit analysis. It aids in the planning for upgrades or new construction. It helps right-size defensive forces, and also supports technology evaluations. It was probably not till about 5 or 6 years ago that the commercial nuclear power plants started using these tools. And what they found was that some of the things that they thought were the reasons things happened in their protection program weren't quite what they actually thought. For example, if they were running a force-on-force exercise and one of their guard force members was killed, simulated killed in that exercise, they assumed that it was due to a lack of training or improper training. When they started running the computer models, they found that these same people that were being killed in the force-on-force exercises were the same ones that were being killed in the modeling. And what that led them to better understand was that their protection program was probably not designed the way it should have been. It wasn't necessarily training, but rather in the development of their protection program. So these things can be very helpful. The other thing that we found when they started using these tools was that post 9/11, every year before they had their force-on-force exercise, they would start ramping up security, putting in new security features, adding guard positions and things of that nature, not really understanding how all of these elements work together, but hoping that if they put the additional features in, that they would have a better chance of winning their force-on-force exercise. When they started modeling them, they started realizing that they had a lot of positions that weren't really contributing to the overall system effectiveness of the security program. And in the end, they've been looking at trying to reduce some of these positions and eliminate some of these positions because it doesn't really benefit them. Every ghost typically costs a nuclear power plant somewhere between $500,000 and $600,000 every year on a continuing basis to maintain that post. Oops. Okay, then what I want to sort of end this on is essentially one of these policy questions that I actually conducted a workshop, and one of your professors, Vicki Buer, actually participated in that workshop last month. Was why should we try to find an approach to quantify likelihood of attack? One of the things you typically find is that in the general nuclear world, people say, oh, well, the security people just assume that an attack's going to happen. And so that's always caused me concerns as a statistician, because I look at it as a conditional rather than an absolute. So essentially, what is the environment we're living in right now? Virtually all people say that it cannot be done. Most people believe that the security community promotes the concept that we should assume that an attack will happen with certainty, giving the impression that security is conservative to an extreme. If an attack happens somewhere, a knee-jerk reaction takes place and security is ratcheted up, often to an extreme. We saw this as a result of Oklahoma City, the first World Trade Center attack, and then the 9/11 attacks. And essentially, security goes up, but we never see it come down. Once security increases, it's very difficult to reduce it, and there's no ability to compare safety and security risks. And in the end, I think that's probably the biggest concern I have, is that we don't really know the difference or how similar those two risks really are. Operational benefits. It would allow us to better allocate resources between safety and security. It would provide useful information to support licensing submissions when changes in safety or security are proposed, and would also enable vendors to develop reactor designs that balance safety and security risk. Policy benefits. It would enable the Commission to better assess when security requirements are adequate in the context of risk. It would provide more information to support better risk-informed decisions. It would enable the Commission to balance safety and security requirements in the context of risk. The Commission would need to determine if safety and security risks should be comparable or if one should be lower than the other. It would enable better determinations on security plan reviews and force-on-force outcomes, and would give the Commission more insight in how to allocate resources between safety and security. But how can it be possible to achieve? Well, one of the problems we face is that as statisticians, scientists, and engineers, we seek to reduce uncertainty, creating estimates that are very precise and unbiased to the extent practical. It can be difficult to change that focus. We have to be able to step back from our textbooks to address these challenging problems. What are we really trying to achieve? Are relative comparisons the approach we should consider? And actually, in the workshop that we conducted last month, people tended to believe that the relative comparisons might be of significant value. And do our quantifications have to be plus or minus 0.01%? And in the end, I would suggest not. Some thoughts on how to approach the problem. We should be trying to understand if our risk is really in the ballpark of where we would like to be. We understand that uncertainty is forever changing as to the actual value. But that should stop us from using it to support risk-informed decision-making. If we can get a general sense of how security risk relates to safety risk, we will be far ahead of where we are today and in a much better place. So how large an uncertainty can we have to support risk-informed decision-making? I guess I tend to be on the other end of the spectrum, and I suggest that there may even be benefits if we have an uncertainty up to 1 and 2 orders of magnitude. It would allow us to at least make necessary comparisons that can't be made today. And the discussion will continue. My suggestion is that we need to think outside the box. Let's take advantage of insights that we can derive from information sources such as the University of Maryland START program, which looks at open source terrorist type initiatives and activities. Let's throw away the textbooks and look at the bigger picture. Let's find a solution to a challenging problem that few people have believed could ever be achieved. So I think that's it. So I guess I'll open it up to questions. We've got about 15 minutes or so that we can ask questions, but I tried to give you a sort of a broad range of different types of risk-informing activities that you might not typically think that exist within the nuclear security community.
Well, great, thanks so much. Really interesting introduction for many of us into this topic. We have one question that's come in here asking about the overlap between design basis threat and design basis accident in a risk-informed decision-making, with the example of an aircraft impact.
Okay, so essentially what happens really, they're done a little bit differently, I think. When you look at design basis accidents, you're looking at sort of the frequency of random events occurring, earthquakes, tornadoes, things of that nature. When you start looking at design basis threat, essentially how that is derived is you conduct a threat assessment, you try to understand what the adversaries are capable of. I can give you an example of one of the last projects I worked with at NRC was looking at drones or unmanned aerial vehicles. And essentially what we looked at there was, is the tactic something that could actually be used? And is it being used somewhere in the world? And the assessment was that, yes, drones and UAVs are being used in battle zones in the Middle East and could conceivably be used at nuclear power plants or Category 1 fuel cycle facilities. And so then the question was, well, is it moving in a direction that might be heading towards the Americas, North America. And the assessment was it's probably moving in that direction. We're seeing use of drones and UAVs in Europe and other places. Maybe not in a violent way, but we have drones and UAVs overflying power plants in France and other places. We have them creating nuisances at nuclear power plants, weapons facilities in the U.S., and things of that nature. So then we look at it and say, okay, what are they actually capable of causing the damage right now that we're concerned about? So we actually conducted an assessment using San Diego National Laboratories, and in the end concluded at the current time, or when the study was done about a year or so ago, that the nuclear power plants were robust enough that it was unlikely that we said there was no risk significant vulnerabilities at nuclear power plants at the current time. But the technology is evolving significantly. And the other thing we found when we did our assessment was that the laws and regulations in the United States don't allow the operators of these commercial nuclear power plants to actually do anything to defend themselves. They can't interfere. It's against the law to interfere with an operating aircraft, and a drone is considered an operating aircraft. So the recommendation we made to the commission was that essentially at this point in time, it was not appropriate to put drones within the design basis threat, but that at the same time that the NRC needed to work with its other federal agencies, to include the Congress, to develop the capability to allow security forces at these facilities to legally respond and react to these devices. So that sort of gives you an idea of how we actually look at the threat and decide whether it fits within the design basis threat.
Okay, thanks. Another question for me is sort of this, and I think you alluded to it, but sort of questions about validation when you're getting to simulation tools and things like that. Obviously, you're trying to analyze events that are rare and maybe have never happened before. So unlike physical simulation, there's no experiment you can really have to validate against. And this is a conversation that comes up often in the work that I do as well when you're trying to look into the future. And if I may, just overlapping with that, you also mentioned how you sometimes get counterintuitive results from the system analysis. And so it sort of undermines your ability to rely on intuition too much just to trust the results. So what are the mechanisms you use broadly, I suppose, to establish confidence in the simulation results as they're emerging?
Okay, if we look at the modeling and simulation that's used for the vulnerability assessments, essentially you're taking the typical security approaches conditioned on the fact that an attack has happened. What is the ability of the system to actually appropriately respond? So it's saying, okay, now let's look at the facility being attacked. We're not asking if it could be attacked. We're saying if it is attacked, how well does the security program actually work? And so those simulations are essentially validated through the use of performance testing of the various security functions, response functions. They're also cross-checked with larger exercises like force exercises to look at where there's consistencies and differences in the results. And typically what you're really looking at, what most people, security managers I talk to that use the modeling and simulation routines, yes, they want to know how effective their programs are, security programs are, but they also want to understand what has to go wrong to make their system fail. And so they'll look at the handful of results that show a system failure and say, what actually made it fail? I didn't know that it could fail that way. And that's where intuition plays a role. And they look at it and say, what are the rules that allowed this to happen? What parts of my security system didn't work effectively? Now is there a way for me to actually make sure that doesn't happen in real life? And so that's a lot of how people use these tools. If we look in the DOE world, I think they have a heavier reliance on these tools actually being a measure of how effective the programs work. On the commercial side, the NRC doesn't quite give them that standing. It's more of a tool that supports the broader analysis of how well things work.
Okay, great, thanks. Are there any other questions from the audience? If you have one, feel free to just put it in the chat window. It looks like there are none more there. So I guess with that, well, thank you again, Joe. Really interesting to learn more about that and put some ideas in my head to maybe reach out back to you as some of the work that we're doing involves in some of the non-proliferation kind of analysis as well. So
yeah, anytime you want to chat, feel free to get in touch with me. You know how to get in hold of me.
all right. Well, thanks so much. If we were live, we'd all be clapping, but that's one of the things that we miss in this platform. So just imagine us all clapping, and thank you very much for your time.
Okay, take care, Paul.
All right. Bye-bye.